Welcome back. This is part 2 of our Veterinary Epidemiology series. And honestly, this is the half that shows up all over the ACVPM Epi exam. Part 1 was frequency and association, incidence, prevalence, risk ratios, odds ratios, study design, bias, confounding. Part 2 is diagnostics and sampling, sensitivity and specificity, likelihood ratios, true versus apparent prevalence, combining tests in parallel and series, sample size, clustering, kappa, herd level test performance, and demonstrating disease freedom. Here's my promise for the next stretch. We're not going to memorize formulas. We're going to derive them so that when you're sitting in the exam and your memory goes blank, you can rebuild the formula from the logic in about 15 seconds. Every single formula in this deck comes from one of two ideas, a 2x2 table or the probability that something is missed. That's it. Keep those two anchors in your head and the rest falls out. Let's get to it. Here's the roadmap for part 2. 9 core topics, and they build on each other, so the order matters. We start with the diagnostic fundamentals from the 2x2 table, sensitivity, specificity, predictive values. Then likelihood ratios, which are just a slicker way of doing the same thing. And we'll use them to move from pre-test to post-test probability, the way you actually think and practice. From there, true versus apparent prevalence, because your test is imperfect and the number you observe is not the number that's real. Then combining tests, parallel and series, and when each one is the right call. Then we shift gears into sampling. How big a sample, why we use p equals 0.5, what clustering does to you, and the finite population correction. Kappa gets its own slot, and we finish at the herd level with herd sensitivity, herd specificity, system sensitivity, and disease freedom. If you're short on study time, the highest yield sections are diagnostics and the herd level material. Let's get started on part 2. Everything starts here. If you learn nothing else today, learn to draw this box. Disease status across the top, truly positive, truly negative. Test result down the side. 4 cells, A is true positives, B is false positives, C is false negatives, D is true negatives. The diagonal, A and D, is where the test got it right. The off diagonal, B and C, is where it got it wrong. Now the key insight, and this is a thing people mix up under exam pressure. Sensitivity and specificity read down the columns. Predictive values read across the rows. Sensitivity is A over A plus C. Among truly diseased animals, what fraction did we catch? Specificity is D over B plus D. Among truly healthy animals, what fraction did we correctly clear? Positive predictive value is A over A plus B. Among animals that tested positive, what fraction are actually diseased? Columns are test properties. Rows are what the result means for the animal in front of you. Say that out loud a few times before the exam. Real tests don't hand you a yes or no. They hand you a number, an OD ratio, an antibody titer, a somatic cell count. Somebody has to pick the cutoff, and that choice is where sensitivity and specificity actually come from. Drop the cutoff and you call more animals positive. Sensitivity goes up, specificity goes down. Raise it and the opposite happens. You're never improving the test by moving the line. You're just deciding which kind of mistake you'd rather make. The ROC curve plots that entire trade-off. False positive rate on the x-axis, sensitivity on the y-axis, and every point on the curve is one possible cutoff. A test that hugs the upper left corner is discriminating well. The area under the curve summarizes it in one number. 1.0 is perfect. 0.9 and up is excellent. 0.7 to 0.9 is good, and 0.5 is the diagonal, literally coin flipping. Exam framing. There is no universally best cutoff. It depends on the cost of a false positive versus a false negative, and on prevalence. Walk the diagram at the bottom with me. The blue curve is the test. Every point on it is a different cutoff, and the dashed diagonal is the coin flip. Slide your finger along the curve with me and say out loud what's happening. As you move right, you're gaining sensitivity and paying for it in specificity. The whole art is deciding where on that curve you want to live. It's the slide that trips up smart clinicians, so let's sit with it. Sensitivity and specificity are both 95% here, a genuinely good test, and we're only changing one thing, how common the disease is. At 1% prevalence, positive predictive value is 16%. Read that again. 5 out of 6 positives are wrong, not because the test is bad, but because there are so many more healthy animals that even a small false positive rate swamps the handful of true cases. At 5%, PPV is 50%, a coin flip. At 20%, it's 83. At 50% prevalence, PPV equals sensitivity, 95%. Notice what NPV is doing at the same time. It's beautiful when disease is rare, and it slides as prevalence climbs. The practical lesson, and this is an exam favorite, sensitivity and specificity are properties of the test and don't move with prevalence. Predictive values are properties of the population and move a lot. Screening a low prevalence population, expect false positives, and plan a confirmatory test. Likelihood ratios are, in my opinion, the most clinically useful thing in this whole deck, and they're much less scary than they look. A likelihood ratio answers one question. How much does this test result shift my belief about disease? The definition is the probability of that result in a diseased animal divided by the probability of the same result in a healthy animal. Now just fill it in. For a positive result, how often do diseased animals test positive? That's sensitivity. How often do healthy animals test positive? That's 1 minus specificity. So positive likelihood ratio equals sensitivity over 1 minus specificity. For a negative result, how often do diseased animals test negative? 1 minus sensitivity. How often do healthy animals test negative? Specificity. So negative likelihood ratio equals 1 minus sensitivity over specificity. With a sensitivity of 0.9 and a specificity of 0.95, positive likelihood ratio is 18. A positive result is 18 times more likely in a diseased animal. Rules of thumb. Positive likelihood ratio above 10 is a strong argument for disease. A negative likelihood ratio below 0.1 is a strong argument against. Actually use a likelihood ratio because this is how you'd reason at the shoot side. 3 steps. Step 1. What's your pretest probability? That's the prevalence in the population this animal came from. A herd with a recent import history might sit around 15%. Step 2, and this is a step people forget, convert probability to odds because likelihood ratios only work in the odds space. Odds equals p over 1 minus p, so 0.15 over 0.85 is about 0.18. Step 3, multiply. 0.18 times a likelihood ratio of 18 gives post-test odds of about 3.2. Then convert back to probability, which equals odds over 1 plus odds, so about 76%. That's your answer. One positive test moved this animal from 15% to 76%. Probability to odds, multiply, odds back to probability. Practice that loop until it's automatic, because the exam loves to hand you a pretest probability and a likelihood ratio and let you trip up on the odds conversion. Honest truth about field data. The prevalence you measure is not the prevalence that exists. What you measure is apparent prevalence, the proportion of animals that test positive. False positives push that number up. False negatives pull it down, and both are happening at once. Let's derive the fix. An animal tests positive in one of two ways. It's truly diseased, and the test caught it, which is true prevalence times sensitivity. Or it's truly healthy and the test falsely flagged it, which is 1 minus true prevalence times 1 minus specificity. Add those, set the sum equal to apparent prevalence, and solve for true prevalence. You get apparent prevalence plus specificity minus 1 all over sensitivity plus specificity minus 1. That's the Rogan-Gladden estimator. Two sanity checks worth memorizing. If the test is perfect, sensitivity and specificity both 1, the formula collapses to true prevalence equals apparent prevalence. Good. And it's only valid when sensitivity plus specificity exceeds 1, which every useful test satisfies. If apparent prevalence falls below 1 minus specificity, your best estimate of true prevalence is effectively 0. Put some numbers on it. 500 animals tested, 130 positive. Apparent prevalence is 130 over 500, which is 0.26, 26%. Our ELISA has sensitivity of 0.88 and specificity 0.92, so an 8% false positive rate. Plug it in. Numerator, apparent prevalence plus specificity minus 1, 0.26 plus 0.92 minus 1 equals 0.18. Denominator, sensitivity plus specificity minus 1. 0.88 plus 0.92 minus 1 equals 0.80. Divide 0.18 over 0.8 is 0.225. True prevalence is 22.5%, not 26. Now verify it forward, because this is a great habit and the exam sometimes asks you to. Take true prevalence times sensitivity, 0.225 times 0.88, that's 0.198, plus 0.775 times 0.08, which is 0.062. Add them and you're back to 0.26. It checks out. Notice the direction here. With a specificity of only 92%, false positives were inflating the estimate. Well, testing is OR logic. Run two tests, call the animal positive if either one is positive. Why does that raise sensitivity? Think about what has to go wrong for a truly infected animal to slip through. Test 1 has to miss it, probability 1 minus sensitivity 1, and test 2 has to miss it too, 1 minus sensitivity 2. Assuming the tests are independent, multiply those. So the probability of being missed by both is 1 minus sensitivity 1 times 1 minus sensitivity 2. And combined sensitivity is 1 minus that whole thing. Two mediocre tests together catch a lot, but there's a price, and the exam will make you pay it. To be called negative and parallel, an animal has to be negative on every test. So combined specificity is specificity 1 times specificity 2. It goes down. You use parallel testing when missing a true positive is the expensive mistake. Import screening, FMD suspicion, eradication programs, disease-free certification. High sensitivity means a negative result really rules disease out. Case testing is the mirror image and logic. You only call an animal positive if it's positive on every test. And typically you only run the second test on animals that were positive on the first. Same derivation style. For a healthy animal to be wrongly called positive, it has to produce a false positive on test 1, probability 1 minus specificity 1, and again on test 2, 1 minus specificity 2. Multiply those and you get a very small number. So combined specificity equals 1 minus that product. Specificity goes up. The cost again is symmetric. An infected animal has to be caught by every test, so combined sensitivity is sensitivity 1 times sensitivity 2. And that drops. Use series when acting on a positive is expensive or irreversible. Culling, trade restrictions, a herd depopulation order. Here's the memory hook I'd take into the exam. Parallel is or and boosts sensitivity. Series is and boosts specificity. Whichever logic you apply, that's the parameter that goes up and the other one goes down. Emphasize because this is the practical decision and it's very examinable. Parallel testing or logic, higher combined sensitivity, lower combined specificity. Choose it when the disease is rare, when missing an infected animal is dangerous, and when your goal is to rule out disease. That is, when the cost of a false negative far exceeds the cost of a false positive. Import screening, pre-movement testing, ruling out FMD in a suspect herd. Series testing and logic, higher combined specificity, lower combined sensitivity. Choose it when acting on a positive is serious and irreversible, when you want to rule in disease with confidence, when the cost of a false positive dominates. Culling decisions, trade bans, individual animal certification. And here's what real programs actually do, which is worth saying out loud. Screen in parallel to catch everything, then confirm in series to weed out the false positives. Cast a wide net, then verify. One more caveat for both. All of these formulas assume conditional independence between the tests. If the tests share a biological mechanism, you'll overstate the benefit. Point with me at the two flow diagrams at the bottom as you say this with me. On the left, parallel. The animal goes into both tests at once and any single positive flags it. On the right, series. The animal moves through the tests one after the other. The second only runs if the first was positive, and it takes a positive on every step to call it. One picture is a fan out, the other is a gauntlet. Kappa answers a question that plain percent agreement can't. How much do two observers agree beyond what you'd expect from dumb luck? Say two pathologists each call about 80% of slides positive. Even if they were both guessing, they'd agree a lot of the time just by coincidence. Kappa strips that out. Build the agreement 2 by 2. Observer A on one axis, observer B on the other. The diagonal cells A and D are the agreements. Observed agreement, percent observed, is A plus D over N. Expected agreement, PE, is what chance alone would produce. Multiply A's marginal proportion positive by B's marginal proportion positive. Do the same for the negatives and add. Then kappa equals PO minus PE over 1 minus PE. Read the pieces. The numerator is the agreement you achieved above chance, and the denominator is the maximum agreement you could possibly have achieved above chance. So kappa is literally the fraction of achievable beyond chance agreement that those two observers actually delivered. Interpretation. The Landis and Cox scale from 1977 is the one the exam expects, so commit it. Below 0 is poor, worse than chance. 0 to 0.2 is slight, 0.21 to 0.4 is fair, 0.41 to 0.6 is moderate, 0.61 to 0.8 is substantial, and 0.81 to 1 is almost perfect. Let's work the example. Two veterinarians grade 100 lesion slides. 30 are positive for both, 55 negative for both, and 15 are disagreements. Observed agreement is 30 plus 55 over 100, 0.85. Expected agreement, A called 40% positive, B called 35% positive, so 0.4 times 0.35 is 0.14, and 0.6 times 0.65 is 0.39. Add them. PE is 0.53. Kappa is 0.85 minus 0.53 over 1 minus 0.53. 0.32 over 0.47, about 0.68. That's substantial agreement. Note that raw agreement of 85% sounded great, and kappa knocks it down to 0.68. That gap is the whole point of the statistic. Switching gears from test to sampling, how many animals do you need to estimate a prevalence? The formula is z squared times p times 1 minus p divided by d squared, and it's worth seeing where it comes from rather than memorizing. Start with the margin of error. D equals z times the standard error, and the standard error of a proportion is the square root of p times 1 minus p over n. Square both sides, solve for n, and the formula falls right out. Now the three inputs. Z is your confidence level. 1.96 for 95%, 2.576 for 99. P is your expected prevalence. If you have no prior estimate, use 0.5 and we'll prove why on the next slide. D is the precision you want, the half width of your confidence interval. And here's the piece to internalize. D is squared in the denominator, so having your margin of error quadruples your sample size. Precision is expensive. Worked example, 95% confidence, expected prevalence 30%, plus or minus 5 points, gives you about 323 animals. Default to p equals 0.5 when prevalence is unknown. Not tradition, it's a one-line calculus result, and it's a satisfying one. Sample size is proportional to p times 1 minus p, the variance term. We want the worst case, the value of p that makes that term as large as possible, because that gives us the safest, largest n. So maximize p minus p squared. Take the derivative, 1 minus 2p, set it to 0, and p equals 0.5. Check the second derivative, negative 2, which is less than 0. So it's a maximum, not a minimum. Done. Look at the table to see how flat this is. At p equals 0.5, the variance is 0.25. At 0.4 or 0.6, it's 0.24, 96% of maximum. Even at 0.3 or 0.7, you're at 84%. It's only when you get out to 0.1 or 0.9 that the sample size really drops. Conceptually, 0.5 is where the outcome is most unpredictable, maximum uncertainty, and any deviation from it makes things more predictable and shrinks your required n. When in doubt on the exam, use 0.5 and say it's conservative. The REST formula assumes every animal is an independent unit of information. In veterinary work, that assumption is almost always false because we sample herds, not individuals. Animals in the same herd share management, genetics, feed, water, and pathogen exposure. So the second animal you sample from a herd tells you less than the first did. The design effect quantifies that loss. DEFF equals 1 plus M minus 1 times the intra-class correlation. M is your average cluster size. ICC is how much more alike animals within a herd are than animals picked at random from the population. Read the extremes with me. ICC of 0 means herd membership tells you nothing. DEFF is 1, no penalty. ICC of 0.1, which is very typical in practice with 20 animals per head, gives a DEFF of 2.9. Typical livestock values run from about 1.5 for low clustering to 3 for high. And the consequence of ignoring it is not cosmetic. Your confidence intervals come out too narrow and your sample size too small. You'd be reporting more certainty than you actually earned. Walk the whole clustering sampling calculation end to end because this is a classic exam problem. Step 1. Get your simple random sample size, z squared times p times 1 minus p over d squared, with z of 1.96, p of zero point 0.3, and d of 0.05. That's 3.84 times 0.21 over 0.0025, 323 animals. Step 2, recognize that independence is violated because you're sampling 20 animals per herd. Step 3, quantify the loss. DEFF equals 1 plus 19 times an ICC of 0.1, which is 2.9. Interpret that. Each clustered animal is worth only 1 over 2.9, about 0.34 of an independent observation. Step 4, adjust, multiply. 323 times 2.9 is 937 animals. That is a serious jump, and it's a real cost of cluster sampling. Two levers if that number is unaffordable. Sample fewer animals from more herds, since M drives DEFF, or find a better ICC estimate from published data for your disease. Population correction is the one adjustment in this deck that gives you sample size back instead of taking it away, so it's a pleasant one to learn. The standard formulas assume an effectively infinite population. When your population is small and you're sampling a big chunk of it, each animal you sample tells you proportionally more because you're removing genuine uncertainty from a finite pool. In the limit, if you sample every animal, there's no sampling error at all. The rule of thumb, apply FPC when n over n exceeds 5%. The adjusted sample size is n times n over n plus n minus 1. Worked example, an island population of 400 cattle, and your SRS calculation demanded 250. 250 over 400 is 62.5%, so absolutely apply it. 250 times 400 is 100,000. 250 plus 400 minus 1 is 649. Divide and you need about 154 animals. You just saved almost 100 head of testing. Order of operations matters on the exam. Calculate SRS, apply the design effect if you're clustering, then apply FPC last. Move up a level from animals to herds, and this is heavily tested. Herd sensitivity is a probability that your testing program correctly flags a herd as infected, given that it truly is infected at or above your design prevalence. P star. Drive it by asking what has to happen for you to miss. Take one animal from an infected herd. It tests negative two ways. It's genuinely uninfected, probability 1 minus P star, or it's infected but the test missed it, P star times 1 minus sensitivity. Add those and it simplifies beautifully to 1 minus P star times sensitivity. That product, P star times sensitivity, is the effective detection probability per animal. Remember it. Now, assuming independence, all n animals test negative with probability 1 minus P star sensitivity raised to the n, and herd sensitivity is 1 minus that. Worked example, P star of 0.05, sensitivity of 0.9, target herd sensitivity of 95%. Effective detection is 0.045, so you need 0.05 equals 0.955 to the n. Take logs. N equals log 0.05 over log 0.955, about 65 animals. Specificity is the flip side, and it's the one people forget until it bites them. It's the probability you correctly call a truly uninfected herd negative. Same decision rule. The herd is positive if at least one animal tests positive. So in a clean herd, no animal is truly infected. The only thing that can happen is a false positive. Each animal tests negative correctly with probability specificity, and the herd is correctly called negative only if every single animal tests negative. Assuming independence, that's specificity raised to the n. That's it. Herd specificity equals individual specificity to the power n. Now feel the sting of that. A very good test with 99% specificity, 30 animals, 0.99 to the 30th is about 0.74. You will falsely condemn about a quarter of your clean herds. Put this next to the previous slide and you have the central tension of herd testing. Increasing N raises herd sensitivity, which is good, but it drives herd specificity down, which is bad. That's the trade-off, and the usual fix is to raise the cut point, require 2 or more positives instead of 1. System sensitivity scales the same logic up to an entire surveillance system. You almost never have one testing program. You have several components running at once. Active herd testing, passive clinical reporting, abattoir surveillance, sentinel herds. Each has its own sensitivity, and each is fairly weak on its own. The key insight: components work exactly like tests in parallel. The system only fails to detect disease if every single component fails simultaneously. So the probability a component fails is 1 minus its sensitivity. The probability all of them fail is the product of those terms, and system sensitivity is 1 minus that product. Run the numbers with active testing at 0.4, passive at 0.3, and slaughter at 0.2. Failures: 0.6, 0.7, 0.8. Multiply. 0.336. System sensitivity is 1 minus that, 66.4%. Look what happened. 3 individually unimpressive components combine into a system that's substantially better than any of them. That's the argument for layered surveillance, and it's exactly why national programs don't rely on a single stream of data. Demonstrating disease freedom is where all of this converges, and it's a real-world, trade-critical application. First, be precise about the claim you're making, because the exam rewards precision here. You're never proving zero infection. You are making a probabilistic statement. With a specified confidence, disease is absent, or if present, it's below a specified design prevalence. 3 parameters have to be defined before you test a single animal. Design prevalence, P star, is the minimum level of infection you want to be able to detect reliably, commonly 0.5% to 5%, chosen based on how bad the disease is and how it spreads. Confidence C is the probability your program would have detected disease if it were present at P star. 95% is standard, and test sensitivity, because an imperfect test must always be accounted for. The model is the same one we've used all day. The probability of detecting at least one positive is 1 minus the probability that all n animals test negative, which is 1 minus P star sensitivity to the n. Set that greater than or equal to C, solve for n, and you get n equals log of 1 minus C over log of 1 minus P star sensitivity. Let's finish the diagnostic story with the question everybody asks. Why do we divide sample size by sensitivity? Compare 2 worlds. Perfect test, sensitivity 1. The detection probability per animal is just P star. With 95% confidence and a design prevalence of 5%, n equals log of 0.05 over log of 0.95. That's minus 2.996 over minus 0.0223. 58 animals. Now an imperfect test, sensitivity 0.8. Your effective detection probability drops to 0.05 times 0.8, which is 0.04, not 0.05. So n equals log 0.05 over log 0.96 minus 2.996 over minus 0.0408. 73 animals, 15 extra animals to compensate for the 20% of cases the test never sees. And the shortcut everyone quotes. For small values, log of 1 minus x is approximately minus x. So n is roughly n perfect times 1 over sensitivity. 58 over 0.8 is 72 and a half. Call it 73. That's why divide by sensitivity works. And now you know it's an approximation, not law. One-page cheat sheet. The slide to photograph before the exam. Diagnostic basis. Sensitivity is true positives over true positives plus false negatives. Specificity is true negatives over true negatives plus false positives. And the Bayes forms of PPV and NPV. Likelihood ratios. Positive likelihood ratio is sensitivity over 1 minus specificity. Negative likelihood ratio is 1 minus sensitivity over specificity. And post-test odds are pre-test odds times the likelihood ratio. True prevalence is apparent prevalence plus specificity minus 1 over sensitivity plus specificity minus 1. Combining tests, parallel sensitivity is 1 minus the product of the misses. Parallel specificity is the product of the specificity. Series flips it. Sample size z squared p q over d squared times DEFF for clustering, and the finite population correction when you're sampling more than 5%. And the herd level. Herd sensitivity is 1 minus p star sensitivity to the n. Herd specificity is specificity to the n. System sensitivity is 1 minus the product of component failures. 3 takeaways for the exam. 1. Almost every formula here is 1 minus the probability everything failed. 2. Sensitivity and specificity belong to the test. Predictive values belong to the population. 3. When you're stuck, draw the 2x2. Good luck. Let's go get that certification. If this helped, please like, subscribe, and share for more.